Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation, and this time my presentation title is Understanding the Nameplate Details of a Power Transformer. My code name is John Kweku Amu-Otu, and I'm a professional electrical engineer for about 30 years, and I'm based in the United States of America. Okay, now let's get to the next slide, and that is the outline of my presentation. So a typical transformer nameplate. The nameplate of a transformer, it's like a birth certificate. Basically, it provides all the information um, based on design, based on factory acceptance testing. That is basically stenciled on um, the plates, and that is basically installed on the transformer. So that basically becomes part and parcel of the transformer for the rest of the operating life of the transformer. So a typical nameplate will have this information, and I go through it. The first one is the name of the manufacturer. So a typical manufacturer, it's ABB Hitachi, General Electric, Siemens. Yeah, just to mention a few. So these are the major transformer manufacturers that are out there. And another manufacturer is Virginia Transformers and Georgia Transformers as well. Sometimes you can have um, the OEM, the manufacturer of the transformers, basically um, basically have a subsidiary that will perform the design of the transformer, and the design documentation will be sent to the manufacturer that will basically manufacture the transformers. Next is the date of the manufacture of the transformer. Usually it is stenciled in the month and the year. So for example, if the transformer was manufactured in October 2022, you'll see that they've written 10/2022 on the nameplate. Next is the serial number. So the serial number usually is what the manufacturer provides that basically gives you all the information about the transformer, the design of the parameters, the factory acceptance testing parameters. Yeah. So once you plug in the serial number, definitely it's going to give you everything about the transformer in terms of design and testing of the transformer. Next is MVA or KVA rating. Right? So the MVA or the KVA rating, as you know, transformers are output rated, right? So because the reason being that they are output rated at MVA is because the connected load power factor varies. So you cannot basically have a transformer that is going to be rated in megawatts or kilowatts. It has to be rated in MVA. Comparably to a generator, right? Okay, so a generator, basically you're operating the generator at a given power factor, right? Okay, so that basically provides you the leading or the lagging, right? Capability in terms of reactive power flow, right? So knowing the power factor and knowing the MVA, that is why generators are megawatts rated. So that is the difference between a generator rating and a power transformer rating. Okay. Next is the voltage rating. Okay, so you can have a high side voltage rating and a low voltage side rating. So a typical example is for a sub-transmission level step-down transformer that steps the voltage from 345 kV to 13.8 kV. It's the high voltage side is 345 kV and the low voltage side is 13.8 kV. Similarly, if you have a transformer that steps down the voltage from 345 kV to 69 kV, which is the typical sub-transmission level voltage, the high voltage side is 345 kV and the low voltage side is 69 kV. On the other hand, you can have a generator step-up transformer, right? That basically steps up the voltage from a lower voltage to a higher voltage. And these are typical examples of transformers that are integrated to generators. So they step the voltage up from 30.8 kV or 18 kV. You know, that is mostly what I've seen in the industry and I've worked on in the industry. They step the voltage up to either 230 kV or 345 kV transmission level voltage. So the high side voltage is 345 kV or 230 kV, and the low voltage side is 13.8 kV or 18 kV, depending on the type of voltage that this transformer have. Next is the frequency, and as you know that the nominal frequency that we have is either 50 Hz or 60 Hz. That's basically what is known all over the world. Next are rated currents. So you'll see the rated currents are based on the rated MVA. Next is the number of phases. As you know, we have a single phase transformers and three phase transformers. So you'll see it on the nameplate, whether it's a single phase transformer or a three phase transformer. Next is oil temperature rise above ambient. Okay, so in designing power transformers, right? Okay, so an average ambient temperature is chosen, and typically it's about 30 degrees Celsius. That is the average ambient temperature that is used in designing all transformers. And basically, in the past, or many decades ago, or right from the 40s, the 50s, the 60s, transformers had an oil temperature rise above ambient of 55 degrees Celsius, based on typical insulation material that were used in those days, right? But nowadays, about a decade ago, most transformers that are designed have 65 degrees Celsius. So that itself tells you that a lot of work has been done in basically having a robust insulation system to achieve that 65 degrees Celsius oil temperature rise. So you'll see that on all those older transformers, you see that ambient temperature rise is about 55 degrees Celsius, and the newer ones 65 degrees Celsius. Similarly, for winding temperature rise above ambient, right? In the older transformers, you will see that it is stenciled 55 degrees Celsius. But in the newer ones, based on robust insulation system, thermally aggregated paper that has been used in the design that can withstand higher temperature and thermal stress, you'll see that most of the transformers that had been manufactured a decade ago have 65 degrees Celsius stenciled on the nameplate. Next, as we continue on the outline, basically for the cooling class, we have different nomenclature based on whether the transformer is from Europe or from United States of America. In United States of America, it's basically based on the ANSI standard, and mostly in Europe, it's the IEC standard. So they have different definitions for the cooling class. Okay, so OA means open air, and that's an ANSI nomenclature. And what it is saying is that the transformer is self-cooled, right? Okay, so the oil, as the transformer is in operation, right? Okay, and the oil gets heated, right? It expands in volume, and basically through convection, the transformer, the hot oil, rises up naturally and flows through the radiator. So air that is flowing on the surface of the radiator, the radiator itself has thin walls, right? Okay, so and has a larger surface area. So if you have a natural air that is flowing on the surface of the radiator, it basically is able to remove all the heat that is in the oil. As such, the oil that is basically gets to the bottom of the radiator that is ready to get back into the transformer has been self-cooled. So that is what they call the open air or self-cooled transformer. Next is forced air, right? Okay, so AF is also an ANSI nomenclature, meaning that it is has directed cooling, right? Utilizing stage cooling fans, right? Okay, so you have fans that are mounted on the surface of the radiators, and you can have multiple of them depending on the size of the transformer. You can have stage 1, stage 2, stage 3. I've basically run into bigger transformers that have us all the way up to stage 4 transformers. cooling fans. Right? Okay, so and what the cooling fans do is they blow air based on the load, increasing load, right? As the transformer picks up load, then basically the fans, based on the temperature that is being, the set point that is being sensed by the set points, then these stage fans come on to basically blow over the surface of the radiator to remove the heat from the oil. So the oil that flows through the radiator and gets to the bottom is cooler and ready to get inside the transformer to basically repeat the cycle. Right. Next is Onan. Okay, so Onan is an IEC nomenclature, right? Like I mentioned that we have the ANSI that is North American, and IEC that is more European standard. Okay, so Onan means the oil is flowing naturally, right? There's no forcing in it, right? Okay, so the oil is flowing naturally inside all the ducts, inside the active component of the transformer. And as the oil heats up, it expands in volume, and hot oil rises up through a convection action, and it flows through the radiator. And the natural air that is flowing over the surface of the radiator is the one that removes the heat from the oil. So the oil that gets to the bottom of the radiator, ready to get inside the transformer to repeat the cycle, is cooler than the oil at the top of the radiator. Okay, AN means that the air is flowing naturally. It means that you have natural flow of air over the surface of the radiator. There are no fans. Okay, so that is what Onan means. It means oil, natural, air, natural. There is no forced cooling in that cooling class. Okay, so next is ONAF 1, ONAF 2. Yes, so like I indicated, sometimes you, depending on the size of the transformer, you can have two-stage cooling fans. So this is a typical example of a two-stage cooling fan, ONAF 1, ONAF 2. So if a transformer picks up load, okay, you have the nominal MVA rating, right? Okay, and that basically corresponds to Onan. So let's say you have a 30 MVA, that corresponds to Onan. So ONAF 1 will be about 33% more than Onan rating. So 33% more than 30 MVA. So let's take, for example, that is about 45 MVA, right? So ONAF 1 will be 45 MVA. So that is when the transformer has picked up enough load within that area. So that is when the first stage cooling fans comes on, based on the temperature, the winding oil temperature that has been measured and detected. So that basically turns on the fans, the stage cooling fans. So ONAF 2, similarly, that is the second stage cooling fan. So let's say ONAF 2 is upgraded, at 60 MVA. So when the transformer picks up more load and up to 60 MVA, so that is when this stage cooling fans come on. So it means that if the transformer picks up load from 45 MVA up to 60 MVA, two stage cooling fans come on to blow cooling air over the surface of the radiator to remove all the heat that is in the oil, so that the oil that gets to the bottom of the radiator is much cooler, right? Okay, so ONAF 1, ONAF 2. So ON means the oil is flowing naturally. There's nothing forcing the oil through the ducts and the active components of the transformer. AF means it's forced air, and forced air means we are utilizing the cooling fans to blow over the surface of the radiator to remove all the heat that is embedded in the oil. Next is ONAF rating. So this is also a typical example of an IC nomenclature. Okay, so OD means directed oil, right? Okay, so depending on the size of the transformer, and sometimes during design of the transformer, it becomes necessary that the temperature rise above ambient for oil and winding is not being achieved, then that is when directed oil utilizing a pump is used to be able to pump the oil through all the ducts to remove the heat as quickly as possible to meet the temperature rise above ambient design for oil and winding. So OD means we are utilizing a pump, right? That is located outside the transformer. Usually you see the pumps located right below the radiator. That is pumping oil into the active component. So the oil is forced through all the ducts inside the winding to remove the heat as quickly as possible. Next is AF. AF means that the air is forced. So in addition to that, if the transformer picks up additional load, then that is when the stage cooling fans comes on based on the measured temperature by the top oil temperature indicator. Next is OFAF. OFAF is also another IEC nomenclature, right? Okay, so in this one, it means that the oil is forced and the air is forced. So I'm utilizing a pump to force the oil, and I'm also utilizing a fan to force the air over the radiator to remove the heat. Next is OFWF, right? Okay, so this is also another typical transformer cooling class rating. That it means that the oil is being forced utilizing a pump, right? But with regards to removing the heat, the oil goes through a heat exchanger. So there is a water that is being forced flowing in a different direction to the oil that is flowing in a heat exchanger to remove the heat from the oil. Next is ODWF. Okay, so similarly, I'm using a directed oil flow into the active component, and I'm utilizing water in a heat exchanger to remove the heat from the oil in a heat exchanger arrangement. Next is de-energized tap changer, right? You see all the tap changer taps, right? Okay, so a typical example for de-energized tap changer is plus or minus 2.5%. It means that above the nominal rating, you have 2 taps above and 2 taps below. So total number of taps is 5, right? Okay, so that allows the variation of the voltages on the high voltage side. Remember, the de-energized tap changer is mostly located on the high voltage side, and the transformer has to be de-energized before you can change those taps. Next is an on-load tap changer. Okay, so a typical example for an on-load tap changer is plus or minus 16%. Okay, so that means a total number of taps of 33 taps, right? Okay, so you have 16 taps above the nominal and 16 taps below, right? So including the nominal is about 33 taps, and the on-load tap changer for ANSI design of a transformer is located on the low voltage side, but for IEC design it is mostly located on the high side. Next is the vector configuration or the phase shift, right? Okay, so a typical example of a vector configuration is DYN1, right? Okay, so capital D means that the high voltage side winding is connected in a delta configuration, and the low voltage side is a Y that is grounded, right? Okay, and the 1 is basically the phase shift between the high voltage side and the low voltage side. Okay, so it means that the high voltage side is leading the voltage side by 30 degrees. 1 means 30 degrees based on the clock system. Between 12 o'clock and 1 o'clock, there's a 30 degrees angle between 12 o'clock and 1 o'clock. Next is a percentage impedance, right? Okay, so you see it, and the percentage impedance is basically the factory acceptance testing results, not the design, right? Okay, so that is what you see on the transformer, the percentage impedance, and the impedance is basically measuring the leakage flux that flows through open areas in the active areas of the transformer. Next is the weight, right? Okay, so the weight, you see the approximate weight of the power transformer. That is the total weight. Then you see the oil volume, right? You see the oil weight as well, and the quantity of oil, either in pounds or either in gallons or liters. Next is the untanking weight. Untanking weight means that if the top cover has been removed, all the bushings has been removed, then you have a total of the oil inside the tank and the active component. So that is the untanking weight. Then you can have the weight of the core and core. That is the active component. Right? Then also you can have the maximum and the minimum pressure of the oil preservation system. Okay, so for a sealed type of transformer, you have a nitrogen blanket that has been provided on top of the oil. The goal is to create a positive pressure so that it prevents or mitigates external contaminants from intruding into the oil, right? If you have an external contaminant, let's say oxygen, nitrogen, getting into the oil, basically it's going to degrade the oil and it's going to create an oxidation inside the oil, right? So the goal is to create a positive pressure over the oil, and we utilize a nitrogen cushion on the oil. So you have a maximum and a minimum pressure that you need to achieve. You also see the liquid level at 25 degrees, and basically this is a standard that has been achieved, utilized worldwide. Okay, so the transformer is basically filled under vacuum at a temperature of 25 degrees Celsius. So that corresponds to a level of oil in inches, right? Okay, so 12 degrees C filling corresponds to, let's say, 12 inches of oil that is inside the transformer. Next, we'll take a deep dive into an actual nameplate that is on a typical transformer. Okay, so as you can see over here, right? Okay, so the manufacturer is McGraw Edison, right? And they are based in Pennsylvania. I think this manufacturer has been bought by Siemens also, and I don't think that McGraw Edison is in business now. Okay, so this is a typical three-phase transformer. So remember, I made mention that you can have either a single phase or three phases. So in this instance, it's a three-phase transformer. Right? Okay, so if it is a single phase transformer, you see it stenciled on the nameplate. Okay, so then it provides the voltage rating. Okay, so this particular transformer, it's 115 kV voltage rating for the high side, right? And that is the line-to-line voltage, right? Okay, so for the winding voltage, which basically it's basically on the phase to ground, right? It's 115 kV over root 3, and that is given by 66.4 kV, right? So your high voltage winding has been given in line to line and line to ground, or phase to ground, which is basically the winding voltage. So the dash is basically what separates, as you can see over here, the dash is what separates the high voltage side and the low voltage side, as you can see over here. Yeah, this is the high voltage side, and this is the low voltage side. So the high voltage side is 115 kV line to line, and line to neutral is 66.4 kV. Okay. So now let's talk about the low voltage side, right? Okay, so for the low voltage side, you have a 21 kV transformer that is connected in a Y configuration. The high voltage side is connected in a Y configuration, as you can see over here, right here. This is a Y configuration for the high voltage side, and For the low voltage side, there's a Y configuration and solidly grounded. So the HO is the neutral that has been grounded, and the XO is the neutral that has been grounded. Okay, so the low voltage side has a line-to-line voltage of 21 kV and a line to neutral, which is basically the winding phase voltages, that is 12.12 kV, right? So the phase voltages are like this. It goes across the phase A, phase B, phase C, right? Okay. So, like I made mention that this particular transformer is a 3-winding transformer and has 3 windings. So the first winding is connected in the Y configuration, and the neutral is grounded. The second winding is also connected in the Y configuration, and the neutral is grounded. The third winding is a delta winding. Okay, so for this type of configuration, we utilize a delta winding called a stabilizing winding. So the goal of this delta winding, it has 3 functions. The first one is to stabilize the voltages between the high side and the low side. So this is the delta tertiary winding, or the third winding, and its goal, like I said, the first one is to stabilize the voltages in the high voltage side and the low voltage side. The second function is to basically provide a path for tripling harmonics, third harmonics. And a third function is to block zero sequence currents due to single line to ground faults, right, on the high side or the low voltage side, or double line to ground fault on the high side or the low voltage side, right? So it blocks the zero sequence current if a fault should happen on the high side or the low voltage side, so that the zero sequence current will not interfere with the protected relay that is located either on the high side or the low side. So these are the 3 functions of the delta winding stabilizing winding. It is usually the corner of it is grounded. Okay, so the goal is to basically stabilize the overvoltages that can occur due to the stray capacitance from this because it has a high impedance, right? So the corner of it is grounded so that it prevents overvoltages and basically can destroy the insulation that is wound on the winding. So now let's talk about the MVA rating, right? Okay, so like I indicated that a transformer can have multiple ratings, MVA ratings. So this one has 225 MVA, or 225,000 22,500 kVA as an open air rating. That's a self cooling rating, right? Okay, so for this rating, basically the transformer is operating without any forcing of oil, right? It means that the oil expands in volume as it gets heated up. Then the oil rises up due to a convection actions and flows through the radiator. There's a butterfly valve on top of the radiator, and it flows through the radiator, and basically naturally flowing air basically goes across the surface of the radiator to remove the heating that is from the oil. Next is the second rate, right? Okay, so it means that the transformer has picked up load. So we go to the second one, right? So that is at 30 MVA, right? So we are moving from 22.5 MVA to 30 MVA after the transformer has picked up load, right? So as the transformer has picked up load, it means that we need to basically implement the first stage cooling fans based on measurement of the top oil temperature. So as the top oil temperature measures the temperature, and the transformer has picked up load from 22.5 MVA to 30 MVA, then the first stage cooling fans comes on based on a set point that has been recommended by the manufacturer. So you see the set points in the oil temperature gauge, utilizing a needle that is shown in the gauge. Then we have a third MVA rating, right? Okay, so that is 37.5 MVA, right? So if the transformer picks up additional load, that is when the second stage cooling fans comes on based on a temperature set point from measuring the top oil temperature, right? So at this stage, you have two-stage cooling fans that comes on. The first stage cooling fans is on. The second stage cooling fans is on. So you have all this forced air that is blowing across the surface of the radiator to remove all the heat to make sure that the transformer is able to achieve the oil temperature rise above ambient. If it is at 65 degrees Celsius, it's able to achieve that and basically maintain below that temperature rise by design. And also the winding temperature rise, if it is 65 degrees, make sure that it achieves that. So in this case, it is 65 degrees Celsius, as you can see over here, right here. So that is your design temperature rise, right? Oil temperature rise and winding temperature rise. So I have the first stage cooling fans and the second stage cooling fans on to remove all the heat to make sure that my temperature rise is below 65 degrees Celsius. Because if it goes above 8, then you are not meeting design criteria. That is when you will develop hot spots. Okay, so I made mention that we have a de-energized tap changer, right? Okay, on the high voltage side of the transformer, right? And this is shown over here, right? Okay, so you have a plus or minus 2.5% above the nominal tap rating, and plus or minus 2.5% below. So you have a total voltage variation of 5% on the high voltage side, right? That is, you can, let's say if you have 115 kV as your nominal voltage, right? You can have 2.5% of voltage above it and 2.5% of voltage below 115 kV. So this tells you all the voltages that can be achieved based on that voltage variation utilizing the de-energized tap changer or offload tap changer, right? And it tells you all the currents that can be achieved, right? Okay. Then the different tap positions from tap A, B, C, D, E, shown over here, right? And this is all the currents and all the voltages due to that voltage variation. Okay. Next, I made mention that the serial number, right? Okay, so the serial number is shown over here, and this is stenciled or etched on the nameplate. This basically provides you an insight into the design and testing parameters of the transformer. Okay, so next is the liquid level change per 10 degrees Celsius liquid temperature change, right? Okay, I made mention that the transformer, the liquid level, the transformer is filled at room temperature of 25 degrees Celsius. Oh, this is a standard that has been utilized worldwide, right? Okay, so the height of the oil that is inside the transformer will correspond or be proportional to 25 degrees Celsius, right? So the transformer manufacturer will also provide an indication that for every 10 degrees Celsius change in oil temperature, this is the level of oil change. So let's say if the transformer expands in volume, right, and changes temperature, let's say from 25 degrees Celsius to 35 degrees Celsius, then the liquid level is going to change by, let's say, 2 inches. Next, it's the weight, right? like I made mention that we can have different weights indicated for the core and coil, right? For the tank and its fixtures, right? For the on tanking, um, when the top members are removed from the transformer. Then you can also have an indication of total weight. This information helps with transportation. This also helps with having the right foundation for the transformer to be located on, to be mounted on, to be installed on. This is also a good information for the structural engineers. Okay, so next is the basic insulation level, right? Okay, so the basic insulation level, it's basically the dielectric strength that of the insulation for it to withstand the lightning impulse surges, switching impulse surges, and power frequency over voltages, right? When the transformer is in operation. Okay, so the high voltage side has a design basic insulation level, right? And the low voltage side also has that, and the tertiary winding also has that. Next is the winding material, right? Most often than not, the winding material for the power transformer is copper. And for the high voltage side, it is copper. For the low voltage side, it is copper. And for the tertiary winding, which is the delta connected winding, it is copper. If the transformer is wound utilizing aluminum, you'll see aluminum over here. Next is the impedance, right? As you can see over here, this is the impedance that is settled on the nameplate after performing the factory acceptance testing. This is not the design impedance. The goal of the factory acceptance testing is to meet the design criteria. But most often than not, after performing the factory acceptance testing, the impedance that is measured deviates from the design by, it should be within plus or minus 7.5%, right? So what is obtained after performing the factory acceptance testing is what is stenciled or etched on this nameplate. Okay. Next it's the winding arrangement. As you can see over here, right? The high voltage side is designated by H1, H2, H3. So H1 is phase A, H2 is phase B, H3 is phase C, right? Okay, so this particular transformer has only one bushing located below the top compartment. So this is where basically the bushings go through the bushings. So this is a typical bushing type of cities, right? Okay, and rated at 600:5. So as you can see over here, the high voltage side, it's Y wound, and the neutral is grounded. So this is the neutral, right? As you can see over here, the H0. And the neutral city is also 600:5. So this neutral city basically goes below the bushing and is located in the bushing turret. It's a TURRET. Okay, so as you can see over here, like I made mention that this transformer, the high side is connected in the Y configuration and the neutral is grounded over here. Then the low voltage side, the first secondary winding is also connected in a Y with the neutral grounded, right? As you can see over here, this is the neutral that is grounded, right? Then we have phase A, phase B, phase C cities that are located below where basically it encapsulates the bushings. Yeah, basically the bushing goes through the center of those cities. Okay, so the low voltage side winding has basically two cities, right? Okay, so the first city, it's 1200:5, right, in each phase. And to be able to determine the winding temperature of the transformer, a typical CT is utilized. So this CT called a hotspot. Basically, it is used to measure the hotspot temperature. So the current that is going through this CT basically is wired through a, um, a winding resistor, a heater, basically that mimics the heating of the load. And this is basically an adder is basically added to the measured temperature of the heater to determine the winding hotspot. So a temperature gradient basically is added to the temperature of the heater to achieve the hotspot temperature of the transformer. So this is a typical CT that has been installed in each phase to be able to determine the winding hotspot. So there are two components that you utilize to determine the hotspot. The first one is utilizing the CTs that are located in the low voltage winding in each phase that basically mimics or basically determines the amount of current that is being carried by the load. And this current, these CTs are integrated to a heater. So that heater basically heats up and mimics basically a corresponding temperature. Then there is a gradient temperature that is added to the measured temperature from the heater, and that determines your hotspot temperature. Next, we'll go to a typical nameplate of a two-winding power transformer, right? Okay, so this transformer is a 50 hertz transformer, as you can see over here. Okay, so that is the frequency, right? And it's a three-phase transformer, right? Okay, so this transformer has three ratings, right? As you can see over here, the OA rating, that is the open air. It means it's a self-cooled transformer, right? Air is flowing naturally over the radiator. There are no fans, right? Right? That's this rating over here. Then the second rating is forced air. So that is when the fans that are located on the radiator are turned on, the first stage, right? As you can see over here, forced FA. Then the second stage is forced air and forced air. So this transformer has pumps, right? So there is a pump that is forcing the oil that comes on, that forces the oil through the active component, the ducts, to remove the heat faster, right? Then also it has forced air. So you have a second stage fans that come on, right? So you have two-stage cooling fans that are come on at this stage. Then you have a pump that comes on to remove the heat faster because the transformer has picked up bigger load. As you can see over here, we'll walk through the MVA rating at each stage. Okay, so now, right here, this is the serial number of the transformer. So like I indicated, this is etched, stenciled on the nameplate. Remember, I made mention that the nameplate is the birth certificate of the transformer. This basically becomes part and parcel of the transformer throughout the operating life of the transformer. Even after the operating life, if the transformer is salvaged, this serial number becomes part of the transformer. Okay, so now let's go to the voltage rating, right? The voltage rating is shown over here, right? Okay, so we have the high voltage side that is shown as a 23 kV voltage. So the high voltage side is rated at 23 kV. So the dash here, as you can see over here, is what separates the high voltage side and the low voltage side. Okay, so the high voltage side has a low voltage winding rated at 13.8 kV, right? That is the line-to-line voltage, right? But to neutral or line to ground or line to neutral voltage of 7.97 kV. So this is the phase to neutral or the winding phase voltage. And this is the line to neutral voltages, right? So I've explained to you how the high voltage side winding voltage looks like, and the low voltage winding, how it looks like, and what separates them. The dash is what separates the high voltage side and the low voltage side. Now, let's talk about the MVA rating, right? I made mention that this transformer has a self-cooled rating. Self-cooled rating means that it has no stage cooling fans that has been turned on. There's the possibility that the stage cooling fans are installed on that transformer, but they have not been turned on. It is utilizing natural flow of air to cool, to remove the heat from the oil, right? Okay, so this transformer has a self-cooled rating at 12 MVA continuously at 65 degrees Celsius, right? Okay, so the MVA rating is what you can achieve. You can achieve a 12 MVA at 65 degrees Celsius. Temperature rise above ambient for oil and winding temperature. So this is the first stage rating. Now let's talk about the second stage. So the second stage is 16 MVA. So this transformer has the capability to achieve a forced air cooling of 16 MVA continuously if the top oil temperature rise above ambient is maintained at 65 degrees Celsius, both for the top oil and winding temperature rise above ambient. So this is when the first stage cooling fans come on, based on the measured oil temperature rise. Next one is the third one is the MVA rating at forced oil and forced air, right? Okay, so this is shown at 18 MVA, right? Okay, so this is when you have your pumps coming on, forcing the oil through the ducts of the active component of the winding. The active component is a combination of the winding and the core material, and basically the supporting clamps that is clamping their active component together to withstand short circuit forces. So this is when the forced oil, the pump is on, and the second stage fans are on. So at the third rating, you have three things going on. You have the first stage cooling fans coming on, the second stage cooling fans coming on, and the pumps are on. The goal is to forcibly pump the oil and to remove the heat from the oil, and also push the air to remove the heat from the oil. Next is the impedance, right? It is shown over here. So the impedance is basically from the factory acceptance testing results, right? After you simulate both the total loss, which is a combination of the no load loss and the load loss, the copper loss, right? And the no load loss is your magnetization core loss. Okay, so the impedance is shown at the ONAN or AOA rating. That's the base MVA rating. That is how the impedance is shown, and it is also shown at the base kVA rating for the high side and the low side. So as you can see over here, the base rating for the high side is 23 kV, and the base low voltage rating is 13.8 kV. So that is what the impedance is shown, right? And the base MVA rating is 12.5. Okay, so now the high voltage winding capacity. Okay, so the high voltage winding is rated at 23 kV for the high side, right? Okay, so this is the amount of amps that can flow for the high side. Okay, so this basically gives you an indication of how much any connection that is connected, any cabling or leads or the bushing that is connected to the high voltage winding, the amount of current that it can handle and the amount of voltage that it can handle. Okay, so now let's talk about the BIL, basic impulse insulation level, BIL. That is the capability or with the withstand strength of the insulation, both paper and oil, to withstand dielectric impulses. That is lightning impulse surges and switching impulse surges and power frequency over voltages, right? Okay, so for the high voltage, we have H1, H2, H3, right? Okay, this is the amount of voltage that the insulation system, both paper and oil, has been designed to withstand. Next is the low voltage side, X0, X1, X2, X3, right? It can withstand a basic insulation level of 110 kV, both for the high side and the low voltage side. So now let's talk about the winding configuration. Okay, so the high side is connected in the delta configuration, right? As you can see over here, right here. And the low voltage side is connected wound in a Y configuration with the neutral grounding. The neutral leads are brought up to be grounded, right? Okay, and the material for the winding is copper, right? Okay, so for the low tap changer, right? The low tap changer has on-load tap changer connections, right? Okay, so it utilizes a reactor or preventative auto transformer. Basically, that is more of a reactor that allows all the taps to be achieved. So this basically it's the low tap changer, on-load tap changer. So on-load tap changer means that all these tap positions can be changed and can be achieved while the transformer is in operation. So the difference between on-load tap changer and de-energized tap changer is de-energized tap changer, which is located on the high voltage side. The transformer has to be de-energized, has to be isolated before you can change the de-energized tap changer. The de-energized tap changer basically varies the voltages on the high voltage side, and the on-load tap changer varies the output voltages on the low voltage side. Next is all the currents that can be achieved based on the MVA. Next is basically all the tap positions, right? Remember, I made mention that it's 16 taps above and 16 taps below. So basically a total of 33 taps. Okay. Next is the winding arrangement, right? Okay, so your high side winding is wound in the delta. So as you can see over here, this is a delta configuration over here, right? And this winding has CTs. Basically, you have CTs that are used for mirroring and protection, right? Protection relay to protect the transformer, to provide a mirroring instrumentation on the transformer, right? Okay, so, and I made mention that de-energized tap changer, that is plus or minus 2.5% above and below, providing a total tap position of 5, are located on the high side. So this allows you to vary all the taps on the high voltage side to achieve the variable voltages that you need to vary to achieve on the high side to be able to maintain the required input voltages to achieve the required output voltages that is meant for the load. Next is the low voltage side. The low voltage side is wound in a Y configuration, as you can see over here. Right. And like I indicated, to achieve all these taps, right, the low voltage winding is integrated to a reactor called a preventative auto transformer that allows you to achieve all these tap positions. So the tap section is what is shown over here, right? These are all the taps. the low tap changer, basically. These are all the arrangements of the low tap changer, right? Okay, so like I indicated that when a transformer is filled with oil, right, they fill the transformer under vacuum at 25 degrees Celsius. This is a standard that is utilized worldwide, and the goal is to have a standard liquid level rating for the oil liquid level indicator, right? Okay, so what they are providing here is they are indicating that for this amount of temperature change, when the transformer picks up load, is in operation, it's going to expand, right? The temperature is going to change, right? Okay, so for this amount of temperature change, this is the liquid level that changes in the transformer. So basically, it's a variation of liquid level in proportion with ambient temperature, 25 degrees Celsius, that room temperature that is used to fill the transformer under vacuum. Next, it's another deep dive into a typical three-winding power transformer. Okay, so as you can see over here, this transformer has three winding. Okay, so winding 1, winding 2, winding 3, right? Okay, so winding 1 is wound in Y with a neutral grounded. Winding 2, it's wound in Y with a neutral grounded. Okay, so winding 1 is the high voltage side, right? Okay, winding 2 is a secondary winding, a low voltage winding, and winding 3 is a tertiary winding, or secondary winding. The goal, like I made mention, that the goal of this winding, tertiary winding, is it provides three functions. The first one is to provide stabilizing voltages for the high voltage winding and the low voltage winding, as such that the voltages that are in the high voltage winding and the low voltage winding is maintained at the right level. The second function is to block 10 harmonic currents, right? Tripling harmonic currents. It blocks it so that it doesn't interfere with your measured currents that basically will be utilized by your protected relaying, and basically it's more of a power quality measures. The third function is to block zero sequence current. Let's say for a single line to ground fault that occurs on the low voltage side, it prevents that current, the zero sequence current, from interfering with the protective relay that are located on the high voltage side. Vice versa, for a single line to ground fault on the voltage on the high side, it blocks the zero sequence current from interfering with the protective relays that are located on the low voltage side. Next, let's take a look at the high voltage winding. Okay, we have like I made mention that the high side is wound in a Y configuration with the neutral brought up and grounded. Okay, so we have cities that are embedded, located below below the flange of the top of the transformer, right? Okay, so the bushing basically goes through the center of this bushing type of city, right? Okay, so this city can be used for protection or for mirroring, right? So we have one city that is located in the neutral. So as you can see, this I'm pretty much sure this city is used for ground fault protection for the power transformer. So it is either a 51N or 51G or 50N or 50G. Next is phase A, right? Okay, so phase A has 3 cities, as you can see over here. So we can have some of the cities that are used for protection. Some of the cities can be used for mirroring, right? Okay. Then we have the de-energized tap changer. Remember, I made mention that the de-energized tap changer is located in the high voltage side and has 5 taps. right? Tap A, B, C, D, E, right? Okay. And C is the nominal tap. So we have A, B above, then D, E, F below, right? Okay. So next is phase B, right? So phase B also has three cities, right? Okay. So these cities can be used for protection and mirroring. Next is phase C, right? And also has three cities, right? These cities can be used for mirroring and protection. Okay. So we have the high voltage side connected in the Y configuration, as you can see over here, right? With the neutral brought out to be grounded. Okay. Then the low voltage side is also wound in a Y configuration, but the low voltage side is where the on-load tap changer is integrated, right? Okay, so the low voltage side, this is the neutral of the low voltage side, has a CT that is in there to be used for protection. Then the phase A of the low voltage side also has a CT. Phase B also has a CT. Phase C also has a CT. Okay, so this CT can either be used for protection or can be used to mimic or determine the hotspot temperature, like I indicated in the previous slides. Basically, it measures the load current, and this load CT is integrated to a heater. And the measured heating element, the temperature, it's basically a gradient is added to achieve the hotspot temperature, right? And the on-load tap changer taps utilizes basically PA, a prevented auto transformer, which is more of a reactor to achieve all the tap positions that is in the load tap changer compartment to achieve to vary the load voltage side voltages that is to be utilized by the load, right? Okay, so this is all shown over here, right? Okay, over here. Okay, and also shown over here. And for the high voltage side, all the taps, all the 5 taps are shown. Right? Tap 1, tap 2, tap 3, tap 4, tap 5, right? Tap 3 being the nominal tap, right? So you have 2 taps above, 2 taps below, right? Okay, so 1 and 2 taps are above, and 4 and 5 are taps below, with tap 3 being the nominal. So nominal means that that is where it's going to show you your basically your nominal voltage. So if the nominal voltage is 115 kV, that tap 3 is, it will give you that indication. Okay, all right. So basically, you know, a bird's eye view basically gives you basically the arrangement of how the transformer is looking on top, right? Okay, so this is where the load tap changer is located. This is an arrangement of the high voltage and the low voltage. Okay, so this is where the bushings go through, the bushings go through, bushings go through phase A, B, C, and the neutral of the low voltage side, phase A, phase B, phase C. Okay, right. Okay, so then over here, right? Okay, so this is the delta winding, right? Remember, I may mention that the corner of the delta winding is grounded. The goal is to basically mitigate over voltages that can occur due to stray capacitance from the insulation. If that is not done, it is basically going to burn the insulation. The insulation is going to fail due to over voltage condition. So we corner ground the delta winding, and that corner ground is brought out of the tank on top of the tank. So you see a typical bushing for this tertiary winding. Okay. Next are the weights. So basically, this is an indication of the weights, right? Okay. So as you can see over here, the first one is the untanking. That is when the top part of the bushing is removed with all the bushings and the flanges and all the devices that are located. A typical example is the pressure relief devices. That is when you, this is the weights you're supposed to have. Tank and fittings, right? Okay, so tank and fittings is when you have the tank and all the fittings are removed, are integrated, are all together. That is the radiator, the control cabinets, and all the auxiliary devices, all of them. So this is the weights that you're supposed to have. Next is the main tank, the oil, right? Okay, like I mentioned, 30,000 gallons, right? And the weight in pounds is shown. Okay, so this information basically helps during the transportation of the transformer when the oil is drained and put in gallons, right? To know the amount of weight. Right? So next is this one is for the main tank, and this one is for the low tap changer, right? Okay, so the low tap changer has 360 gallons of oil. The main tank has 13,000 gallons of oil, right? And the weight for the low tap changer is 2,700 pounds, and the weight of the oil is for the main tank is 97,500. Then the total weight of the transformer is 306,200. So the structural engineer, this is the weight that the structural engineer needs to build a foundation, by adding some contingency in it, some other, let's say 5 to 10% contingency. Next, like I indicated, a transformer oil is filled under vacuum at a room temperature of 25 degrees Celsius in the factory, right? And at 25 degrees Celsius, this is the level of the liquid. Okay. Then they also provide the changes in the liquid level. So this one is saying that 1.17 inches. If you have a temperature change of 10 degrees Celsius, let's say the transformer picks up load, right? The oil hits more, expands in volume, right? So it's going to change by this amount based on a 10 degrees Celsius. Likewise, if you have the transformer contracting in volume during winter time, right? When the transformer load goes down, right? The transformer contracts in volume. So based on the outside temperature, right? And the changes in the level of the oil can be determined based on the 10 degrees C change that has occurred. That is the transformer outside temperature is measured utilizing all the temperature indication oil temperature devices that is located on the transformer. Next, I may mention that we have a preservation system, right? We have the nitrogen blanket that is located on top of the oil, especially the seal type of transformer. We have utilized a nitrogen blanket to create a positive pressure on top of the transformer. And what does this mean? It means that I'm creating that positive pressure to prevent external contaminants, weather elements, from intruding into the oil to oxidate the oil, to basically degrade the oil, right? So what I need to do, this is the pressure system of the nitrogen blanket. It means that it has a minimum pressure of 0.5 psi to 8 psi. So this is the range of pressurized system of the nitrogen blanket pressurized system you have to maintain to ensure that positive pressure is maintained as a cushion blanket to maintain that positive pressure. Right. Okay, so if you're filling the transformer under vacuum, remember I made mention that we fill the transformer under vacuum to mitigate gassing, right? Gassing oil bubbles that can degrade the transformer insulation system, right? Okay, so a vacuum is maintained, and this is the amount of vacuum that the manufacturer is telling you to maintain, right? To prevent that gassing and bubbling that can degrade the insulation system when the transformer goes into operation. With that comes the end of my presentation, and thank you so much for your great listening ears. And look out for the next presentation coming from me. And as usual, if you like this presentation, don't hesitate to select the like button and the subscribe button in YouTube. With that, thank you so much.